started. Okay, recorder is already started. So we are going back, to the caller call Lee agreement first, and then we'll talk about local variables today. Yep.
Can you fix the link to calling and returning from subroutines? It doesn't work.
Oh, this one?
Yeah.
Oh, okay. So let me check that. Okay, so it doesn't link to. Okay, let me change that. Wait, that doesn't seem right. Okay, let me fix that. And that part is correct. Okay, so we'll do an update. This one, right? Okay, let me just. Yeah, Canvas is kind of interesting. Well, buggy because when I update something, I actually have to refresh the page before it takes into effect. So let's try that. It's over here. Okay, now it works. But thank you for letting me know. All right. Okay, cool. So this thing, if you look at it now, it actually has syntax highlighting even in TTP ASM code. So I kind of fixed that. It took me a little bit of time to figure out how to do this because this syntax highlighting is specific to TTP ASM. So most of the syntax highlighter that is included in the processing of Markdown does not include syntax highlighting for this one. So I have to figure out how to get around the whole thing. But it's working now, which is good. All right. So what we'll be doing today is to start with a caller-callee agreement. So this may be one of those modules where you want to kind of, have a hot link to, from somewhere else, because we'll be talking about this, from time to time. So what the focus today is on local variables, because we have already talked about parameters, we have already talked about return values. So today our focus is going to be on local variables, and also generally speaking, what is a more systematic way to get to the items that we need to access from the subroutines perspective. So when we look at all the local variable aspects, so on the caller side, there's nothing here. Okay, so if you look at the caller side, there is nothing here that mentions anything about the local variable of the callee. That's because, well, local variables are called local for a reason, because nobody else is supposed to know about anything about the local variables of a function. So the caller has absolutely no knowledge whatsoever, and nor should it care about the local variables of a function that it is going to call. So that's the first part that you have to kind of remind yourself of. But from the callee side, there's quite a bit of stuff that we need to worry about. So additional stack may be utilized for local variables, and the callee is also responsible to deallocate any local variable that the callee has allocated. But how you want to allocate for the local variable, there's no standard because it's not part of the agreement. Okay, so if you think about the agreement as an interface between the caller and the callee, well, if the local variables are not going to visible, it's not going to be visible from the caller's perspective, why would it show up in the agreement? It's kind of like a rental agreement, right? So what does the rental agreement would specify? It will specify when you're supposed to pay rent, okay, how much, what is the rate of increase, maximum rate of increase per year, etc., etc., etc. Okay, but what is not in the rental agreement is when are you going to wake up and have your breakfast? Why would the landlord care about when you're going to wake up and have your breakfast? It's not part of the agreement. So for the same reason, anything that has to do with local variables is not a part of the caller-callee agreement. Okay? So that means this particular module is not going to help describe what we need to understand about local variables. So if that is the case, then what else? Well, as it turns out, there's another module here that specifically talk about parameters and local variables. So this is the module that we'll also be looking at for today's lecture. Um, okay, so I need to fix this one too. I just changed it this morning and I forgot to append the file name at the end here. Okay, so I need to append MD. I tested the HTML, the URL, separately, but I forgot to update this one to also include the HTML file. All right, the the link, before, link to some other document, which is the same content, but this one is on GitHub. So now it should work. Let me give it a try. It's still not working. Why is it not working? Oh, because I missed a slash. Okay. I do apologize for missing the slash between here and here. There we go. Okay, now I have to refresh again. Alrighty. So let's try that one more time. Okay, third time should be is working. Okay, thank you. All right, so here we go. Let me get rid of these two 404s. There we go. All right. So now we're going to take a look at this part we have talked about already. How do we call a function and how do we push the arguments? So in this case, 5 is the second argument. It is pushed first. So this 5 is pushed by these 3 instructions. The 3 is our first argument. It is pushed last. And as a result, this code here is used to push the first argument in the function call. And then we have to push the return address, which is the last thing the caller has to push. So that is done by these 3 lines of code that pushes the return address. Now, the pushing of the return address, there's nothing in the C code corresponding to it because that is not something that is expressed in a high-level programming language. So the high-level programming language does not need to be concerned about pushing the return address, but because we are working with assembly level code and a RISC architecture at that. So that means we are responsible, the programmer is responsible to push the return address. And then at that point, we can go continue execution at the function that we are calling. When the function returns, it's going to return to wherever the return label is. And at that point, we have 2 increment Ds here because there are 2 parameters that are still sitting on the stack, but the call is already done. Why do you want to keep the arguments on the stack when the callee has already returned? So that means the caller is responsible to deallocate for the arguments that it pushed earlier for the function call. So let me just kind of pause here and see if we are doing okay with this code, because this is what we have already talked about. So this is more or less a kind of recap of what we have already introduced in this class. So do we have any questions? Yep. Go ahead. Nope, not 3 times, because who is responsible to pop the return address? The callee. So by the time we get back to return address, the return address, on the stack is already popped by the callee. So why is it like this? Because it is the convention. That's just really the convention. Yes. Well, but let's take a look at how we have done this before already. The answer is yes. Okay. So I think it might be helpful to kind of review the content from previous classes, because I don't mind answering these questions, but what I need to mention is these are the things that we have already talked about. So the retention from what we have already talked about in the past is kind of important in this class. All right, so Now we are going to take a look from the callee's perspective, that will also answer the question that you asked earlier. So this is the perspective from the callee. And let me just kind of scroll this so that we can show both the assembly code and the C code. So this is the C code, which is really simple. All we are doing is a subtraction. We do need to access the um, parameters. So we are subtracting parameter y from parameter x, and in the assembly code, the first thing we do is we copy the stack pointer to register C, because we don't want to increase the stack pointer, because anything below where the stack pointer points to can be basically trashed asynchronously. So we want to keep that um, fence, okay, where it is, unless we are really sure that whatever is pointing to is not needed anymore. Then we can move the fence so that, okay, you can trash this location all we want because we don't need it anymore. So this is the usual code. Okay, this is one kind of code to access parameter x. So if you follow the comment here, this is when the value of parameter x is loaded into register A. And then by the time we are done with these two instructions, the value of parameter y is loaded into register B. So we have the value of parameter x in register A, the value of parameter y in register B. So when we subtract register B from register A, we just end up with what x minus y should be. And it is also convenient that register A is also the register that we use to return a scalar value, which in this case we have a scalar return value. So after that, we have to pop the return address from the stack, and right here we can see that the increment D is part of the callee's responsibility is to pop the return address, and then after that, register B has the location of where to continue execution in the caller, and the JMPB is going to be the last instruction from the callee's perspective. So this is kind of the same kind of a recap of what we have already talked about, just presented in a slightly different way. Do we have any questions about this portion? No questions? All right. So if there are no questions about this, then we're going to move on to the next section, which talks about local variables. So the local variables of a function are allocated on a per invocation basis on the stack, much like the parameters. In other words, in a certain sense, okay, parameters and local variables are kind of the same thing because they are both on the stack. Then what are the differences? Well, there are two major differences. The parameters are pushed by the caller, okay, because only the caller knows the value of the parameters, because after all, the parameters are a way for the caller to communicate something to the callee. Is that making any sense? Okay. The local variables, on the other hand, is completely allocated by the callee itself because the caller does not need to know. Okay, you may have some local variables, you may not have any local variables. The caller does not need to know. So in terms of who is pushing or allocating the space on the stack, these two are different. Parameters are pushed by the caller, local variables are quote unquote reserved by the function being called. Is that okay? But also because of that ordering difference, because we push all the caller push all the parameters first and then the return address. So the return address actually forms it's kind of like a border between the parameters, which is at a higher location, and the local variables, which is at a lower location compared to the return address. Okay, there's actually a picture or a table that I'm going to show later on. But also because local variables are strictly the responsibility of the callee, so that means the callee, the function being called, is responsible to allocate and deallocate the space used for local variables on the stack. Are we good with that so far? At least conceptually. Okay, so I'm not showing you the code to do it yet. I'm just talking about conceptually, are we understanding that the stack space used by local variables is up to the function being called to allocate and also to deallocate. We good so far? All right. So the next section has a lot of code, okay, because I'm trying to show you a very mechanical way to access items on the frame. So the first sentence starts with the parameters, the return address, and all the local variables collectively is called the call frame, or otherwise just known as frame, of an invocation of a function. So I'm just going to highlight the sentence and stay with this for a little bit, right now. So basically, a call frame, or just frame, is referring to everything on the stack that is needed by an invocation of a function. So I'm just going to pause with that sentence, okay, and see if there are any questions about that sentence. I specifically mentioned an invocation of a function instead of the definition of a function. So what is the difference? Okay, what is the difference between a definition of a function versus an invocation of a function? Yes, an invocation is when it is being called, which means you can have definitions of 200 functions in a program if you want, but you may call only like 2 of them. So in a certain way, the definition of a function is analogous to a class definition. You can define, like a bazillion classes in your program, but your program may not consume any space if you're not making variables out of those classes. Is that okay? But when you make a local variable out of a certain class, then you're making an instance, okay? But that instance does not exist until the function is called. Is that okay? All right. So in this case, I have to emphasize that we are dealing with an invocation, which means if you're dealing with something that is recursive, you can have multiple frames on the stack at the same time, because every invocation creates its own frame. So if the function itself is recursive, then you can have multiple frames corresponding to the same function on the stack at the same time. Now, just because they're all existing on the stack at the same time does not mean that you need to find all of them at the same time. You only need to find the most recent frame, which is establishing the context of the function that you're actually in that is being executed at the time. Is that okay? All right. I'm just going to pause a little bit more to see if there are any questions about what I just said. Okay. All right. Yep.
So you said every invocation creates its own frame.
Mm-hmm. Yep. So I can illustrate that later, okay? Because I need to finish up this part first in order to get to the context so that I can show you what it looks like in Logisim and also what it looks like in the trace. Okay, so because the trace really is the best way to illustrate what do you mean by a frame? Okay, from what location to what location and what exactly is in the frame. So once we get to that point, we can point out, kind of visualize what is in the frame. All right, so we are moving on. From the perspective of the callee, the parameters and return addresses, the return address are already pushed on the stack at the entry point. That's per the agreement between the caller and the callee. Okay, we have already talked about this in the previous lectures. Okay, it is the responsibility of the caller to set up the parameters and also the return address from the perspective of the function being called. However, a callee is responsible to allocate and deallocate for its own local variables. So now the question is, what do you mean by that? So we're going to take a look at a function, just a shell of a function. I just called it function SumFunc, okay, because I did not feel very creative today. So I just called it SumFunc, okay, that's the name of the function. So the way this works out on the stack is the parameter z, y, and x, and also the return address, these 4 items were pushed by the caller. So by the time I get to the entry point of SumFunc, I can say, okay, I'm expecting these 4 items on the stack already because that's the responsibility of the caller. Okay, so that's something that we have already worked with from the previous lectures. But then I also have 3 local variables, A, B, and C. So those 3 local variables, or the stack space that I need for those 3 local variables, that's my responsibility as the callee. So I am responsible to allocate for local variable B, C, B, and also A. Okay, but when everything is all allocated, the stack pointer would be pointing to local variable A. Is that okay? Okay. Now, can you make the stack pointer point any lower than that? Yes. Okay. But this is the bare minimum. So, but from the perspective of the offset from where the stack pointer points to, it is pointing, the offset 0 is just my local variable A. At offset 1, we can find local variable B. At offset 2, we can find local variable C. But that's all the local stuff. And then at offset 3, we should find the return address. At offset 4, we should find parameter X. And then at offset 5, parameter Y. And then at offset 6, we should find parameter Z. Is that okay? This is the frame, okay? As far as we can tell from how some func is defined up to this point, this is the call frame of some func. It includes all the locations for the local variables as well as the parameters. Yes?
Just a quick question on that. When you say frame, you're just talking about the actual routine that's going inside
The frame is referring to the portion of stack that provides the context to execute, for a function to execute.
Okay.
So
you're talking about just how it calls the routine.
No, a frame, once again, a frame is a portion on the stack that provides the context in order for a function, the callee, the function being called, to execute. Because in order for a function to work, you need local variables, parameters, and all that stuff. So a frame is a portion of the stack that provides that context in order for the function code to function, to work.
What does that look like?
Exactly that. So everything is relative to the stack pointer. In other words, do I know exactly where local variable A is? No, I don't need to. I just need to know that when everything is allocated, local variable A is where the stack pointer points to. But then how do we find parameter Y? Oh, easy. It would be 5 bytes away from where the stack pointer points to. So everything is relative to where the stack pointer points to. Is that okay? So this is why we can have multiple frames on the stack, because each time we work with the last frame that we allocate, we are not relying on the absolute location. We're only relying on, oh, okay, this is where the stack pointer points to, and based on where the stack pointer points to, I can find everything else that I need in order for the function to operate. Are we still doing okay with that concept? So that's yes, go ahead.
Each a pointer points to a specific location.
There's a what?
There's a new frame being made?
Every time you call a function, after everything is done at the callee, you have a frame.
Okay. Just one frame. It's not like multiple frames for each call.
For each call, there's a frame. So if the function is recursive, then you can potentially end up with multiple frames, depending on at which point of the execution of the program we are talking about. So this is all dynamic. Yep. In other words, you cannot know ahead of time, how much space on the stack is going to be used, because it really depends on the logic of your program. Okay, if you have a recursive function, then it depends on how deep the recursion can go. If the further or the deeper the recursion can go, the more frames you're going to have to create, and so on. Is that okay? So there's code and then there's space, okay? The code is the actual mnemonic that describes the action that a function needs to do, but the data is providing the context, which is all the parameters and the local variables that we need in order for the code to work. So are we doing okay so far with those two concepts? More or less. Okay, all right. So from the callee's perspective, this is okay. This is starting to get a little bit interesting. Is we can keep using this approach, okay, the one that we used earlier, which is basically just dynamically calculate the address of all the parameters, and now we can include that with all the local variables. But it's a very brittle kind of code, okay? I call this kind of code brittle because if I were to add one more parameter, or if I change the ordering of the parameters, this code is it's not gonna work, okay? I have to go to the entire program and really read line by line to kind of make all the adjustments, okay? On the other hand, the new approach, which is to use the labels to indicate the offset to each item on the call frame that I need access to, is just using labels. So in this case, okay, let me see if I can show both the table and the label definitions at the same time. So in this case, you can see how this is at offset 0 from where the stack pointer points to. So I can now just define a label of some func underscore a and a 0 to basically use a label to remember not the location of where I can find local variable a, but the offset from where the stack pointer points to find my local variable a. Is that okay? In other words, this 0 is corresponding to this 0 here in order to find local variable a. But it's only relative to where the stack pointer points to. And I have no idea ahead of time where the stack pointer is going to point to when the function is called. But I should not care about that either. Are we doing okay so far with that? Yes?
Does that mean that local variable size pointing to the return address?
No, it is not pointing to the return address. It is the offset to the return address. Yep. So we have to be very careful with what we say, because when we say the address of, that means we know exactly where it is. But when we say it is the offset to from where the stack pointer points to, it means I don't know exactly where it is, but I know if I can have the stack pointer, then I can find it. Yep. All right, so the next line is mysterious, okay, because it is using what I call a postfix notation. So some func b is a label definition. We can tell it's a function definition. I mean, it's a label definition because of the colon. Okay, so any identifier followed by a colon is a label definition. But the value that is defined to looks kind of funky because it's some func underscore a, which is the label that we defined earlier, and then the 1 plus. That is called postfix notation. So I know most people in this class have never been exposed to postfix notation. So I'm going to go back to the Canvas shell here because there are some resources here that can help you with postfix notation. Here's a link here, okay, that points to postfix notation, which is actually a part of the documentation of the assembler. So it would go straight to the postfix expression and label definition section of the manual of the assembly of the assembler. So right here, there are two resources that can be very useful. The first one is a link to an article that teaches you how to convert from infix notation to postfix notation. Okay, so there's a general approach to do that. Okay, so let me just kind of go to that link here so that you guys can take a look at that particular link. So I'm going to open it in yet another new tab, and this is why I end up with like 40 tabs with the browser, because I keep opening up new tabs, and I usually forget to close them when I don't need them anymore. Okay, so converting infix notation or expression to postfix notation. So this is just an example of how it is done. This is something that is better illustrated if I were to display it as a tree, okay? So we'll go ahead and take a look at something that is more complex. So we'll just say that we need to calculate x plus w, the whole thing, times z, and divide it by 1 plus z plus w, okay? Don't ask me why we are doing this, okay? We'll make this even more interesting. We'll make this a multiplication here. There we go. So do we understand, if I were to give you the values of x, w, z, do you think you can handle this, on the calculator? Okay, because we are used to infix notation. The reason why we are familiar with infix notation is because we have been taught infix notation since elementary school. Okay, the first time you see the addition operator, it is already in infix notation. It is called infix notation because the operator is in, okay, it's between the values that it's supposed to operate on. So when you think about x plus w, okay, the operator is in between the two values that we are supposed to add, which is x and w. That's why it's called the infix notation. To convert this to a postfix notation, you kind of have to think in a slightly different way. Okay, so the way we think about postfix notation is we specify the values that we need to operate on first. Then we specify what we want to do with those values. Okay, in some sense, it actually makes more sense. Okay, in some way, it makes more sense because instead of just giving you one item, tell you what to do with it, and then, oh, by the way, there's one more thing you need to do this. That doesn't seem to make sense in a normal situation. Instead, you might want to say, okay, this is one kind of form, this is the other kind of form, and I want you to do blah, blah, blah with these forms. In other words, I give you all the information that you need, and then I tell you what to do with the information that I provided. Okay, so in a certain sense, your postfix notation actually makes more sense. So to convert this into postfix notation, we specify x, we specify w, and then we say, oh, by the way, I want to perform an addition with those two values that I just gave you. So I specify a plus first then. So with a plus, what happens is it will take these two values, perform the addition, but then the sum is now becoming available. It becomes an item to be operated on later on. So now I say, okay, by the way, there's also a z that I need to give you. So now I have two items, right? Because the sum between x and w is already available, I'm giving you an additional value, which is called z, and I can say, with those two things, do a multiplication, okay? So that means when this is all done, then we have the numerator of the original expression already done. And then what do? We now say, okay, fine, I'll give you a value of 1. What am I supposed to do with 1? Okay, just hold on, okay? I'm not telling you yet, okay? I'm just giving you a value of 1, but don't do anything with it yet because I have not specified the operation. Then I'll give you z. Okay, so this is, I'm running out of space. I'm going to have to, I'll just copy the whole thing down here, okay? So x, w plus z multiply 1 z again, okay? So at this time, this is already resolved. This is the entire numerator of the expression. The one I haven't really told you what to do about it, okay? I'm just telling you that, okay, here's a value. The z, I haven't told you what to do about it. I'll give you even one more thing, which is w. So at this point, I have 4 items that is just sitting somewhere, okay? So there's one word to describe, how we organize all these values. Can someone kind of guess how we are arranging these things? Think about it from the perspective of the order of how we introduce the values and the order of using the values. I heard what fo again? FIFO or LIFO? LIFO, that's right. It is a stack, okay? We're actually using the stack concept in this case to deal with infix notation. So now I have 4 items. 1, 2, 3, 4 items. Okay, I go like, okay, what are we going to do with these 4 items? We now specify a multiplication. The multiplication operation says, oh, there are 4 items here. Which 2 should I multiply? the very last two items, okay? So this multiplication will only perform, the multiplication of z and w. So now we have three items left, okay? The entire numerator, the 1, and then the product between z and w. Those are the three items that I have available. So the next operation is a plus. The plus says, okay, I only need two items to perform the addition. Which two items should I use? These two items. So now we have only two items left, which is the numerator and the denominator. And what do I do with those two items? Just divide them. So that's how postfix notation works. Now, if you're thinking, I'm not feeling very confident about doing all this conversion myself, that's okay. That's if you go to the documentation here, there's also a link to a converter. So let's go to the converter and see what it has here. So we can try to enter exactly the same infix notation, okay? So I need what? X plus W times Z, the whole thing divided by 1 plus Z times W. Okay, I don't think I need that open paren here. Okay, there we go. And convert. Okay, so let's see whether I did the conversion correctly myself. XW plus Z multiply 1 ZW multiply plus and the slash. It's all done. Okay, so am I going to give you something this complex in the final exam just so that I know whether you know how to do postfix conversion? The answer is no. Okay, most of the things I need to do is plus 1. Okay, so that means you just have to say, oh, okay, if I just need to add 1, then I specify what, and then the 1, and then the plus, because that converts into whatever plus 1. Okay. Does postfix sound like something from outer space? Looks kind of alien. A little bit. That's only because your mind have been poisoned since first grade with infix notation, just like our mind have always been poisoned by base 10 numbers. Okay, because does base 10 number make sense? Only when we have no calculators, because we got 10 fingers, okay? So it's easier to work with base 10 when you have 10 fingers. And, only when you work with small quantities where it is usually around 10, okay? Is base 10 useful in huge numbers like billions, since we were talking about billionaires earlier? No, it doesn't help at all, okay? We just feel comfortable because we are taught, using that particular base. If you were taught using base 7 in elementary school, you would have felt comfortable with base 7, but it doesn't make sense. Now, base 2, does it make sense? It actually does, because it is the smallest base that is still useful, but the multiplication table of base 2 is tiny. Think about a young person. Okay, it can be your own children, or a nephew or a niece. Okay, who's just trying to get through learning the multiplication table. The base 10 multiplication table is pretty complex. Okay, and until you master multiplication, you cannot even get started with division. Does that make sense? Okay, so we spend a lot of time trying to memorize, the multiplication table and also the subtraction table. What do you mean by subtraction table? 2 minus 5. What is 2 minus 5? It can be -3, but it can also be 7 with a borrow of 1. But you have to remember those, okay? You cannot just go like, okay, I'm going to try to figure that out, when I'm doing the multi-digit subtraction. You kind of have that memorized. In base 2, what do you need to remember? 0 minus 0 is a 0 with no borrow. 1 minus 0 is a 1 with no borrow. 1 minus 1 is a 0 with no borrow. 0 minus 1 is the only one that is tricky because it is 1 with a borrow of 1. Done. Even for elementary schooler, that will take how much time to memorize? Lunch break. That's all it takes. Okay, it's lunch break. You're done with the whole concept of division. Multiplication table, even easier. 1 times 1 is 1. 0 times 1 is 0. 0 times 1 times 0 is 0. 0 times 0 is 0. Done. That's your entire multiplication table. So the bottom line is this looks foreign only because we were taught the infix notation. Now, why does the infix notation not make sense? Because it needs parentheses. If we are to convert to use postfix notation, there is no need for parentheses anymore, because the order of the operators are already explicit. It's already spelled out. Okay, whatever operation we specify, it works on the previous two values that we have worked out already. So I know, from our perspective, it looks really foreign. We don't think that way, but there's an entire generation of engineers and business people where they have to work with HP calculators. And most of you do not even know that HP used to manufacture calculators, scientific and business calculators. But because the silicon or the processor at the time is kind of primitive, they did not have enough silicon to handle parentheses. So what do you do when you cannot handle parentheses? Postfix notation. Okay, so this is also called RPN, which stands for reversed Polish notation. Now, why Polish? I'm not really sure. Okay, you can probably look it up and find out why it's called reversed Polish notation. But RPN basically refers to this way of expressing, equations and expressions. All right, so getting back to where we are. Okay, so we are only dealing with postfix notation. So can somebody tell me what this actually means? Using postfix notation, we specify the values first, and then we specify what to do with those two values. So if I were to express this in infix, the normal notation, what would that be? It would be sum func underscore a plus 1. That's it. Okay. And for the most part, this is the kind of postfix notation that this class has to handle. So do you guys think you can handle that? Okay, excellent. And if you cannot, there are tools to help you. Okay, you cannot do this during the final exam, but this will get you kind of familiarized with the whole process of doing the conversion. And you can also follow this part over here, which is kind of like a manual method of converting infix to postfix notation. Just in case somebody is thinking, but Tech, you're teaching us things that are useless, because no one uses postfix notation. Our calculator, my TI-84, can handle parentheses all day long. There's no need to use postfix notation. You are correct about the TI-84, but there are programming languages out there where the only thing you can understand is postfix notation. And some of you are already thinking, it's like, Tech, name one. Okay, I can name two. PDF and PostScript. You go like, PDF is not a programming language, it's a file format. No, it is a programming language. Because the way PDF works, okay, for the most part, not entirely all, but for the most part, PDF is derived from PostScript. Okay, they're both products of Adobe. PostScript, POSTSCRIPT, was a quote-unquote language to communicate with a printer. You go like, what does printer have anything to do with this class or postfix notation? So let me ask you this question. How do you convince the printer, like a laser printer, to print whatever you want to print? You go like, we just send a whole bunch of dots over, right? Just zeros and ones should be fine. Well, that's one way to do it. But as the resolution of your printer increases, because right now 600 by 600 is kind of like medium, okay? A lot of laser printers are capable of 1200 dpi times 1200 dpi. That's a lot of dots, okay? So if you need to send over all the zeros and ones, where one is a dot, where there's a carbon, where there's carbon, and zero means you do not deposit carbon, the size, okay, the amount of data that you need to transmit over is huge. If all you want to draw is a circle, you're still transmitting a whole lot of zeros and ones just to specify that circle. And guess what? If your printer changes resolution, your printer driver that is running on your PC has to be aware of, okay, so what is the resolution of this particular printer? Oh, this one is even better. It's 2400 by 2400. So now it has to redo all the calculations in a different way, blah, blah, blah. A lot of recomputation. So what PostScript does, which is also what PDF does, is to specify, you know what? I just need to draw a circle here with a radius of 2 inches, and the thickness of the circle is going to be 0.25 of a millimeter. Okay, that's the instruction that you send over to the printer. Okay, you're just sending out instructions of how to draw a circle. So if you want to draw like a really pattern kind of thing, like just a whole bunch of concentric circles expanding out and blah blah blah, you can actually write a program to do that. PostScript allows you to specify everything that you can do in C++. Loops, conditional statement, function calls, and so on. But guess what? They're all expressed in postfix notation. Hence the name PostScript. Okay? Now, PostScript is something that most of us are not aware of unless you are writing the printer driver for printers. You're not aware of PostScript. But PDF, we do know. Okay? Who in this class does not know what is PDF? Okay, we all know what PDF is, but PDF works the same way. Okay, it is sometimes we just need to send raster data, like from a scanned document. There's no way to get around that one. But when you want to print, like concentric circles and whatnot, you can actually write programs in PDF to draw concentric circles in a loop. Okay, and that is because PDF is actually derived from PostScript. So all this entire discussion is basically saying, oh, so postfix notation is not just something that is kind of cool because this is how we do things in the 80s. Okay? No, this is actually used in industry. Okay? So if there's any question about why the assembler, okay, which is something that I made in the 2000s, why is it also using PostScript? The answer is also easy. Well, I don't have that t-shirt today. It's because I'm lazy. Okay? The parser that I need to understand infix notation is significantly more complex than a parser that is needed to understand PostScript notation. So I just go like, we'll just use PostScript notation because the parser is super easy to work with. As long as I have regular expressions and all kinds of basic tools for text manipulation, I'm done. It's easy. All right? So some of this may come back and be useful later on in your career, and some of these may not come back and be useful. But it is still kind of information that I think, generally speaking, is useful. All right, so having said that, then we go back to the module that we were on and go like, oh, okay, so all we are doing is to define a label sumfunc B is 1 byte after sumfunc A. Is that okay? Which makes sense, okay? Because B, or the offset to B, is at 1, which is basically meaning that, hey, if you go 1 byte above where the stack pointer points to, you're going to find local variable B. What about C? Well, C is 1 byte after B, and that's why it is B1 plus. And then the local variable size, which is the total number of bytes that I need for all the local variables, is just wherever I can find C as an offset from where the stack pointer points to, just add 1 to it. This 1 plus, this 1 of the 1 plus has to do with the size of C itself. In other words, this 1 has to do with the size of A, this 1 has to do with the size of B, this 1 has to do with the size of C. So that's how we can compute the total number of bytes that we need for sumfunc for local variables. Is that okay? All right, okay, cool. So now we can move on to what about the parameters? Well, as it turns out, the parameters can also be figured out about the same way. Parameter x is basically 1 added to the local variable size. So if you look at this picture here, it kind of makes sense, right? Because we have 3 bytes that we need for the local variables. So 3 plus 1 is 4, and guess what? 4 is in fact the right offset, the correct offset to where we can find parameter x. The reason why we need that 1 plus, this 1 here, has to do with the return address taking up 1 byte on the stack. Is that okay? All right. So after that, getting to y is pretty easy because y is right after x, z is 1 after y. So I just use the offset of the 1 plus from each one before that so that I can calculate the offset to each one of those items that should be on the frame. So I'm going to pause a little bit here and see if there are any questions about the approach of how I define the labels as offsets to find the various items in the call frame from where the stack pointer points to. Okay, we're just talking about the approach. Okay, so if there are no questions, then we can now take a look at the shell of this particular sum func. So this is what it's going to look like. The first thing we need to do, now this is something that is new to us because we never had to do this before, because we have never talked about local variables. So now that we have started to talk about local variables, we know it is the responsibility of the callee to allocate for the local variables. This is how we do it. Okay, so LDIA sum func underscore local var size would just use the label that we defined earlier and load that value into register A, okay, which is representing the number of bytes that we need to reserve on the stack for all the local variables. Not for one, I'm allocating for every local variable in, for the entire function. But that's just a number, okay? It's not changing the stack pointer. In order to allocate space on the stack, you need to change the stack pointer. So that's why the next statement is to subtract this amount from where the stack pointer points to. So now I have a chunk of memory that is on the stack that's now allocated. Now, it's allocated but not initialized. In other words, do I know the initial value of local variable A, B, or C? No. It's whatever those 3 bytes turn out to be on the stack. Okay, so they're uninitialized. But do I own that space? Can someone come in asynchronously and start to modify those locations? Not after the subtract instruction, because after the subtract instruction, I moved the fence to include the local variables. So whatever gremlin is going to modify memory locations asynchronously is now fenced off from the local variable space. So we're doing okay so far of how we allocate the space for local variables. Okay, so whatever code we need to write for the body of sum func, we're going to put it here. When we are all done, what do we need to do? Whatever you allocate, you better remember to deallocate. So the code to deallocate that space is simply to move the stack pointer back to where it was before the allocation. So if the allocation is using subtraction, then the deallocation is going to use addition. So note how I use register B over here. Over here, I can use any register I want. But over here, I have to be careful, okay, whether I can use register A or not. In this case, I could have used register A because sum func is a void function. It does not return a value. But in the case where sum func does return a scalar value, how do we return a scalar value again? In register A, that's right, okay? So if sum func does return a scalar value, somewhere here would have specified the return value and put it into register A, and I cannot change register A after that because that's the return value. So that means, okay, out of the other registers, I only have register B and C to play with, after that point. So might as well just kind of make it more or less a de facto rule not to use register A for the deallocation and also the return code at the end of a function. Okay, now do you have to always use register B but not register A? No, but it is safe to use register B or register C for that purpose. So are we still doing okay so far? Okay. So after the deallocation of the local variables, then the stack pointer should now be back to pointing to the return address, because after all, the return address was pushed by the caller. So I can count on that to be on the stack at this point. And then at that point, after that, I just have the usual 3 instructions to pop the return address and then go back to where the return address indicated I should go back to execute programs, to execute in the caller. All right, so I'm just gonna pause a little bit here and see if there are any questions about the template of a function that has local variables. The function is responsible to allocate and to deallocate before the return to the caller. So I know there's a lot of stuff here. Okay, there's mechanical stuff like what instruction to use, what expression to use, and so on. And then there's also conceptual stuff, which is, okay, so what is where on the stack? So what is where on the stack is basically this table over here for the C function that I have defined here. So I'm just gonna see if there are any questions before we can go for a sample program. Yep.
When are we defining local variable size?
So local variable size is defined here.
So where do we put all of these?
Okay, so that's a good question. The question is, where do we place these label definitions? It can be anywhere. I typically put these right after the entry point of a function, but that's just my convention. But label definitions are visible globally, and there's no need to define a label before you use it, before you reference it. So this, for all we care, this can be defined at the bottom of the entire file, but it doesn't make sense. Okay, it kind of makes more sense for these label definitions to be right after the entry point of some func in this case. But there's no restriction as to where you have to put these. And then the other thing is the ordering of these definitions also do not have to be like this. If you want to, you can define some func local var size first, and then C, and then B, and then A, which means you're using labels that are yet to be defined. The assembler will automatically figure that out. Yes.
So when it's allocating for space, some func local variable will have 4 bytes. They will allocate that space.
Nope. It's gonna. Okay. So you tell me, what is the value of local var size for some func? Based on how the labels are defined here, what is the actual value of some func local var size? Yes, it is 3. Okay, because some func A is defined as 0, B is 0 plus 1, which is 1, C is 1 plus 1, which is 2, and the local var size is 1 plus, oh, okay, that's supposed to be an underscore here. So it's 1 plus 2, which is a 3. Let me fix that first, because there's supposed to be an underscore here. I did not put it there. So I can go here, look for some func space C, search, found it, change that, commit changes, and then wait about a minute before it gets updated on the other side. All right. So I also have some exercises later on, but we are probably not going to be able to get there yet today. But what I do want to illustrate is how do we get to these things that we have allocated on the stack. So let me just kind of wait a little bit until it refreshes, and then we'll go ahead and talk about that. Yes?
can we test like the program?
You write some code, okay? You have an idea of what the code should do. You write a code, and then we run it.
Yeah, but like what program can we use for that?
Well, let's go ahead and figure that out next. Okay, that's a good question. So let me refresh this, make sure that the fix is in. Okay, because I don't want. Okay, it's already in here, so this is all good. All right, so we got about 20 minutes left. So let's go for a example. Okay, so we go for a sample program, and I'm gonna go for a text prompt. Okay, let's put it here. There we go. And let's see what I want to do. Okay, I know what to do. So we're going to write a C program and then the corresponding assembly language program. So we'll call this recursive again, recursive.ttpsm, and I'm going to erase the original program and start with a new one. All right, so this time I'm going to write how to compute power of 2, okay? 2 to the power of something, okay? So we'll say uint 8 underscore t power 2, and this specifies the actual exponent, so we'll call e for exponent, and we'll do it recursively. And we'll even use a local variable, just completely unnecessarily, but just for the sake of talking about local variables, we'll put one here. So we'll say uint 8 underscore t result. So now we have to kind of come up with the recursive code. The recursive code goes like this. If e is 0, then result is something. Otherwise, result is something else, and then we'll return result at the very end, like so. All right, can somebody tell me if we're talking about 2 to the power of 0, what is the result of that? Okay, that's just a 1. And what if e is greater than 0? Then result is, okay, remember we're trying to do this recursively. It'd be power 2 e minus 1 times 2. Okay, so is that okay? Okay, so I'll let you guys think about this a little bit, okay, when I work on the main program. So on the main program, I have, I'm going to make a local variable x here, and I'd say I just want to compute, 2 to the power of, say, 5, okay, and then return 0. Okay, that's my entire program. This program should compile, okay, so that means you can use online GDB to find out how this program works, if you were to debug it. So my concern is mostly, okay, if I want to convert this into assembly code, how is that going to work? So I'm going to start with a no op, and this time I'm going to treat main as an actual function. So that means I'm going to call main from this code over here after I initialize the stack pointer. And okay, let me try not to throw in like multiple things at the same time. So I'm going to use the more conventional way of specifying the return address. So that means I'm going to do LDI, decrement D to push the return address, LDA with L1, which is the return address in this case, LDI, A L1, STDA, and then that's the return address. So that means I can do a jump to main at this point. And then L1 is right here. This is where the main is supposed to return. And right here, we have halt instruction. In this case, I'm treating main as just a regular function. I'm calling main from this unnamed piece of code, which is also called the startup code of a C program. Makes a function call to a regular function main. Okay. So now we go to main, okay? So main has a local variable x. So I'm going to say main x is going to be at offset 0. Once everything is allocated, it'll be at where the stack pointer points to. main LVR, LVS, which is local variable size. Okay, I don't want to type the whole thing. So local variable size is LVS. So that's going to be main x1 plus, because the 1 refers to the size of x itself in main as a local variable. So after that, these are just the label definition. So now I need to allocate the space for the only local variable x. So that means I have a LDI A with main LVS, subtract that much from the stack pointer. So now I would have the local variables already allocated. I don't know about you guys, but my typical way of writing a program is if there's a beginning and an end, I would write both first and then backfill whatever is supposed to go in between. So now I have LD, BD, increment D, JMPB. Okay, that's just usual way of going back to the caller. So now in between, I can specify the code which is here. So I need to call POW2 with an argument of 5. What do I do to do that? This has nothing to do with what we are talking about today, but it does have everything to do with what a previous lecture has already introduced. In other words, I'm only concerned about calling POW2 with an argument of 5. How do we do that? Hmm? Okay, so you can describe just the overall concept. You don't have to describe the actual instructions. So what do we do first? What is the first thing we need to do? We push the arguments in a reverse order. Okay, so the push 5 is to load 5 into a register. Register A, B, or C is fine in this case. Decrement D, STDA. That's pushing 5. Then we have to push, that's the only argument that we have. So the next thing that we push is the return address. Very good. Okay, so I'm going to call that L2. Decrement D, STDA. So now we have the return address pushed. And then what do? We are trying to call POW2. So we have pushed the only argument. We have pushed the return address. What do we do next? JMPI to the name of the function. Okay, so JMPI to POW2, which is not defined yet. Okay, I'll define it later. When we come back, we're going to come back at label L2. Do I have anything to clean up in this case? Is something still sitting on the stack that does not serve any purpose at this point? The only argument, okay? The argument of 5 is still sitting on the stack right now, but it does not serve any purpose. So I have to clean it up. How do I clean that up? Okay, quote unquote, clean up, which is to deallocate it. What do I need to do to the stack pointer to basically say, you can move the fence back by 1 byte now because this byte is not really needed anymore. We added, exactly. How much do I add? 1. That is correct. So increment D would clean up the stack. So that is the only thing I need to do for the function call. But now I need to store the value returned by the function call into local variable x. Okay, so now the question is, how do we do that? So I'm going to show you a template of code that is pretty much universally applicable. Once you have labels defined like this, it is easy. Okay, so we put the offset to get to local variable x in a register. Pick any one of B and C. I cannot use A. Why can't I use register A at this point? Because it is still storing the return value. I still need it, right? Because the whole point of this is to store the return value into the local variable x. So I cannot destroy the return value, which is in register A right now. So I only got 2 registers to play with, which is B or C. Well, that's more than enough. I'll use register B. So I'm loading the offset of local variable x into register B first. The way I document this, okay, which can be very useful to you, is register B now contains the address of x as a local variable minus the stack pointer. In other words, it is just an offset from where the stack pointer points to and to the location of x. It is not the address of x, it is the offset to x from where the stack pointer points to. Well, okay, so if I need to get to the address of x, what do I need to do? This is an algebra question. So if register B has this, But all I really want is just this part here. What do I need to do to register B? Add the stack pointer to register B, okay? So we'll go ahead and do that. So we'll say add BD, because what this ends up doing is register B is now what it had before, which is the address of X minus the stack pointer plus the stack pointer. Is that okay? Because the stack pointer is register D. So that means, oh, wait, I think, even with my algebra, I can figure this out and go like, okay, the SP cancels out because subtracting and adding the same amount, hey, they just kind of cancel out. So now register B has the address of local variable X, which is all I need. I don't need to use a load because I don't really care what that location has right now. Okay, local variable X is uninitialized. Why do I need the value of something that is uninitialized? I don't need it. I need to override it. Okay, so that means at this point I can do STBA so that I'm dereferencing B. Okay, but dereferencing B is basically dereferencing the address of X. So once again, we have some canceling because the referencing and the address of are opposite. Okay, they cancel out. So basically what we end up with in this case is it's basically X itself. Okay, the value of X is now getting the return value, which is in register A. So that stores the result into local variable X. And then after that, I'm done. Okay, I never really got to do anything with local variable X, but that's besides the point. Okay. All right, so let me look at the time. Oh, we got plenty of time. So now we go to POW2. Okay, we've tried to implement POW2. Main is already done. So with POW2, I'm going to do the same thing. I'm going to define a bunch of labels so that each item on the frame has its name. Okay, so we have POW2 local variable result that is at offset 0 because it's the last and only local variable that I need to allocate in this case. Then we have POW2 local variable size, which is the offset to the very last local variable that I allocate, plus the size of that local variable. So that's just 1 byte because it's an unsigned 8-bit integer, which uses only 1 byte. And then we have our only parameter, which is POW2 underscore E. That is POW2 underscore LVS, or the local variable size, 1 plus. This 1 is needed because we need to skip over the return address, okay? Because we know the return address is pushed last from the caller. So that means to get to the parameter, which is pushed before the return address, we need to add 1 to skip over the return address. So with these labels already defined, the typical way, once again, is to allocate for the local variable, deallocate for the local variable, and then do the return code. So that's just how I do things. How you want to do your own thing, that's up to you. So I'm just going to subtract dB to allocate for the local variables, and then I'm going to immediately deallocate the local variables and then use the return code down here, LDBD, increment D, JMPB. So now I have the template of the function already done, allocation, deallocation of the local variables, and now in between, I can now reference the labels that I have already defined. So what is the first thing I need to do? Looks like we need to check whether parameter E is a 0 or not. Okay, so we need to get back to parameter E, not the address of, but the value of, right? So the template to do this is to do LDI, pick a register. Okay, A is fine at this point because we are not ready to return the value yet. So LDI A with POW2 underscore E. So it is always useful to comment. Okay, so I will do some of these commenting at least initially, but then later on, if I do not make any comments, you need to add the comments yourself. Okay, because that is part of the process to kind of understand what is going on, is to leave behind the comment so that you can use your own words to describe what is in a register after an instruction. So in this case, after this instruction, A would have the address of local variable E minus the stack pointer. The offset is in register A. Add AD, After this, A would have the address of parameter E, but that's not what I need. I need to know whether the value of parameter E is a 0 or not. So I'm going to do LDA A, so the register A is actually the value of parameter E. So is the comment on line 17, 18, and 19 clear about what register A has for each step in the process? Okay. So since we haven't really run the code, you cannot visualize it, but when we run the code, it will be visualized, okay? So that's the extra reason why you want to comment the code, because when you look at the trace, the comment shows up on column G, okay? So that's a way for you to associate the instruction and what it actually does and what ends up in register A at the time. Okay, so we need to check whether it's a 0 or not. Do we need a compare in this case? Or is there a trick to do this? And what is the trick to do this without using compare? And AA, okay? So and AA is a trick, and then we do a JZI. If it is 0, we go to somewhere. So in this case, JZI is going to go to the then branch. So I'm going to call the then branch pow2 then 0. And I define the label right now, then 0 over here. So that means if I ever get here, that means the register A is non-zero. That means I have to go to the else case. So now I have a JMPI to pow2 underscore, pow2 underscore else 0, which is going to be defined here. Okay, else 0 is here. And then pow2 underscore and if 0 is going to be here. At the end of the then branch, I have to skip over the entire else branch. So I have an unconditional branch to jump to pow2 underscore and if 0. So when did we talk about this structure? You have the then branch, you have the else branch, but at the end of the then branch, you have to jump over the entire else branch. When did we talk about this? Compiling code. Okay, so that's the module that you need to read in order to understand why we structure the code that we do. All right, so now we say, okay, what do we do in the then branch? In the then branch, we just have to specify a return value of 1. I could have just put it into register A, but I need to demonstrate how to use local variables. So I'm going to use that. So I do a LDI A with pow2 underscore result, add AD. So now I'm not writing any comments. So this is up to you to kind of continue with all the commenting so that you can reinforce what you have learned. And then we have ST. Oh, we cannot do ST yet. Yeah, we cannot do that just yet. So we have to do LDIB with 1, STAB. So that would store a value of 1 into local variable result. So even right now, you can see on line 17 and on line 25, the way we access a local variable versus the way we access a parameter are the same, because they are all living in the call frame, and the way we get to those, both of them, is from an offset of where the stack pointer points to. And that's why the mechanism to get to each one of these two items is basically the same. All right, so the else case is the fun part because we have to do a recursive call. So how do we perform the recursive call? You have to think about the ordering of things, right? So you have to think about, we have to get to E first, and then we subtract 1 from that, and then we call pow2, and then we multiply the return value by 2, and then we store that into result. So that's kind of the order of how we need to do things. So we'll go ahead and specify all that stuff here. So at this point, I am going to be lazy, and I'm just going to do a decrement A to get to E minus 1. Why can't I do this now? Okay, I'll comment here, okay? So I will say that A ends up to be E minus 1, but why? How did I get to here? How did I get to pow2 else 0? The only way for me to get to pow2 else 0 is through this JMPI instruction, right? And what do I know at this point? Well, we know A does not equal to 0, but what is in A? A has E. Okay, parameter E is in register A by the time we get to this JMPI instruction. And as a result, by the time we get to this label, register A still has the value of parameter E. So by decrementing A, I actually now have E minus 1 in register A. Then what do? I push it on the stack because this is the argument to this C code here. So I decrement D, STDA. We push E minus 1 on the stack. Then we call POW. So we have LDIA again with label L3 this time. Okay. This is the reason why using label L1, L2, L3 is not a good idea, because if I use the wrong one, the assembler cannot tell that I used the wrong one. But I'm fairly careful right now, so I think I'm good. So this is calling POW2 from inside POW2. When it returns, I have to increment D just like the other one, because I still have the argument sitting on the stack, which I don't need anymore. And now the return value is in register A. How do I multiply by 2? I don't recall having a mult or multiply instruction in the processor architecture. So how do we multiply a register by 2? Add it to itself. Very good. Okay. So multiplication by itself, multiplication by 2 is just adding register A to register A. So now we have 2 times the return value, and then we just have to store it into the result variable. And for that, we're going to do LDB POW2 result add BD STBA. All right, so that is, I think, what we need. We get to the end if here. So that means we now get to this point, we have to return the value of local variable result. Okay, so we just have to kind of put it into register A. So LDIA with POW2 result, add AD, LDAA. That's all we need for getting the return value from local variable result into register A. And then we just use the deallocation code here to deallocate the local variable, and then the return code to go back to the caller of this one. All right, so that's a lot of stuff, and I have no idea whether this is going to work or not. We're kind of running out of time, but I do want to get this, at least give it a try and see whether it works or not. And as usual, I'm hoping that it does not, because if it does not work, I get to show you guys how to debug a program, which is kind of important. Except for people who think they can write code right the first time. Always. That would definitely not be me. Recursive.ttp.asm. And you guys can switch to the assembler if you want to right now. So the code is good, it's running. All right, so let's check. When most people think, please, please, please make it work, cross their fingers, I'm hoping for the opposite. We'll see. Okay, so how do I check whether the program works or not? A few things. Skip all the way to the bottom first. And we want to see that we end up at a halt instruction. Okay, that's good. We only have one halt instruction in the entire program, so it has to be the right one. Then the second thing we want to know is, did we store the right value into the location where we are supposed to store the local variable x of main? So this is where a picture can be helpful. Okay, so let me erase this. You guys can take a picture later on if you want to. Okay, so when we look at the execution of the entire program, this is the stack. This is location FF, which is the last location. What did we use the last location for in this particular program? It is a return address. It's L1, so that we can return to the unnamed code from main. Because main is now just a regular function, it has to return. So this is our return address to the unnamed code. What about the next one? Now we're in main, and main says, you know what? I have a local variable. And what is the name of that local variable? x. So this is the local variable of main. Okay, the location is FE, but it is local variable x of main. Is that okay? So that means whatever POW25 is supposed to return should be stored here. What is 2 to the power of 5? 32. And how do I express 32 as a hexadecimal number? How many 16s do we have? 2 16s, right? So that means 20 is the hexadecimal value of 32. Do you see, can you verify right now on the projector, can you verify that we did store a 32 to the location where it's supposed to go? Yep, it's right here. Location FE stored a value of 20, which is 32. Yes? Hmm? Okay, we need to express 32 in hexadecimal, which is base 16. So this is going back to base conversion, okay? How do you convert the value of 32 to base 16? Hmm? The value of 32 into base 16. What does each digit mean in base 16? Okay, so we know it's 2 digits, okay, because it's 1 byte. This tells us what is the quantity of, what power of 16 do we express here? Okay, which is, so it is specifying how many ones we have, right? What about this digit? This is the quantity of which power of 16? 1. What is 16 to the power of 1? 16. So this tells us how many 16s we have. How do you express 32? In a sum of powers of 16. 16 times 2, very good. So we don't need anything here, but we need 2 of those. So that's why it is 20 in hexadecimal that represents 32 in base 10. Are we okay so far? Okay. So we did store that value. Okay, this is a verification. So the rest of this program illustrates what we are talking about today. Now, I don't have enough time to go through the entire trace right now. So if you want to, you can go to File and then go to Make a Copy and then name this one specifically, after today's date. Okay, so that next time, if you want to kind of experiment or to document this thing, now you have a full trace of the recursive function. It is probably helpful for me to point out where a frame is, okay, because the whole point of this is what is a frame. So as far as main is concerned, the frame consists of 2 bytes. This byte and FE, which is not visible here because we are not storing anything. So location FF and location FE, these 2 is the frame for calling main. Okay, the next frame is going to be a 5 here because that's the argument, another return address, and then a local variable for the callee. So from location FD, FC, all the way down to FB, that is a frame for POW2. And then after that, POW2 call itself, right? So after that, we have this location storing the next call, the argument to the next call, which is a 4, another return address, another local variable. So this is the call frame for POW2 again. And we will have 6 call frames like that on the stack, at the deepest level of the recursion. So this is at location FA, location F9, and location F8. Okay. You guys can say, Tech, you can say all you want. Okay, how do we make sure that this is in fact the structure of the call frames? Well, let's double check. Let's go to location FA, and see what we put at location FA. So we scroll down a little bit. You can also do a search feature. So location FA is indeed having a value of 4. So this is not a direct definitive proof of what I said is correct, but it is a validation of what I said. Is that okay? So this trace is particularly important because it shows you how recursion works. how each time you call a function, a new frame is allocated to store the parameter, the return address, and the local variables that are specific to that particular invocation. And that is entirely separated and independent to all of the other invocations from before. Is that okay? So once again, we are expecting 1, 2, and then 3, 4, 5, 6. There should be 6 of these. So that means there's a total number of how many bytes being used on the stack. 2 bytes for main, 3 bytes for each call frame of POW2, but we have 6 of those. So 18 of these, 2 of this. So we have 20 in decimal of bytes that should be used. So that means the stack pointer should go all the way down to what? We would have used 20 bytes on the stack. So that means we are looking at 100 in hexadecimal minus 220, and 20 is 14 in hexadecimal. 0 minus 4 in hexadecimal is okay, so this is really testing by base 16 subtraction. So this would be a 12, but the 12 is a C. So, and there's a borrow from this one. So this is 0 minus 2, which would make this an E. And there's a borrow here. This will make that a 0. So that means the stack pointer should go as low as EC before it unwinds and go back up again. So how do we double check that? Well, we track how we change the stack pointer. Okay, so we will it will keep decrementing because we keep allocating more and more stuff because we are basically calling the function over and over again until it stops at some point. Okay, so EF is as low as it gets. And I got EC, so I'm off a little bit here. Darn it. Why is it? Okay, I have to figure out why I got the math wrong somewhere. But but this concludes the lecture. I'm gonna give you guys some extra time for the lab because I just kind of overran the lecture portion. So let me pause the recorder and I'll push it on the